in this video, I'm going to be talking about the law of reflection and the law of refraction. The law of reflection simply says that the angle of incidence is equal to the angle of reflection. Okay. One thing we need to be aware of is that when we measure angles from a normal. So if this is our surface, a normal is a perpendicular to that surface. So that dotted line represents my normal, my ray of light. If it comes in like that, this would be my incident angle right there. And that would be my reflected. So the angle of incidence is equal to the angle of reflection. So if the angle of incidence is 40 degrees, the angle of reflection is 40 degrees. Notice I could easily turn these around and let the arrow go this way and this way. Anytime we're doing a ray diagram with light, the path is completely reversible. If the light had come in from the other direction, it would follow the exact same path. There's two types of reflection that I want to mention. When light is incident on most surfaces, most of the time we get something called diffuse reflection. That happens when something is microscopically rough. If something's rough on a microscopic level, like this, it may feel smooth, just like this sheet of paper here feels smooth, but if I looked at it closely, it's really not smooth. So even if I have a bunch of parallel rays of light, when they hit that surface, the law of reflection will send them off in some pretty random directions, depending on what their angle of incidence is on that rough surface. And as a result, you can't look at it and form a clear, sharp image. Okay. Now, if something's extremely smooth, we get specular reflection. Specular reflection occurs when we have light that's incident on something like a mirror or a piece of glass. Water, like a very still pond or a piece of polished metal. Anything where you could look and see your reflection, that's an example of specular reflection. In specular reflection, microscopically, it's really still very smooth. And so if we have a beam of parallel rays, they will in fact all reflect in the exact same direction. And it's this very sharp, predictable reflection that allows images to form. And when we look at mirrors in a little bit, we'll look at how different types of mirrors and lenses can form images. Okay. For right this minute, that's going to take care of reflection. We're going to come back to it though. when light enters a new medium from, we're going to let it start in air or vacuum, two things happen. One, it slows down. And two, it refracts. Refraction is another word that means that it bends. Okay. I'm not going to spend a lot of time right this minute explaining what causes it to bend, but we can come back to that idea and discuss it. How much it slows down depends on how optically dense the material is. And we define that with something called the index of refraction. So the index of refraction for an optical medium. Generally, an optical medium means a medium that allows light to travel through it. Glass, water, alcohol, plastics, all kinds of plastics and glasses, quartz, different materials that are transparent or semi-transparent that light is going to travel through. Okay. The symbol for the index of refraction is simply a lowercase n, and it is equal to C over V. C is, of course, the speed of light in a vacuum. And V is the speed of light in the material, or in that particular medium. Notice, since the fastest speed will always be the speed of light, it slows down in mediums. This always gives us a number that is greater than 1. Here's a list of some common. Air has an index of refraction of 1.00. If we went out a little bit farther, it would have another digit or two eventually. So it's a tiny, tiny, tiny bit slower in air, but not enough that our index of refraction is anything more than just 1 to 3 significant digits. Okay? Now, if we're looking at water, our index of refraction is going to be 1.33. So light slows down substantially in water. If we look at quartz, we get N equal 1.54. And finally, diamonds are probably the one material that you are familiar with that has a really high index of refraction. Light slows down a lot when it travels through a diamond. Diamond has an index of refraction around 2.42. Okay. You might want to get online and you can Google. I think there are some other materials that do have an index of refraction higher than a diamond. I can't remember their names, and they're not something you would be familiar with, but these are materials you should be familiar with. I know that your textbook will have in it, if you look, a table of the indices of refraction for different materials. Okay. All right. Snell's law. We can also think of this as being a law of refraction. explains what happens when light travels from one medium into another medium. And here it is. NA sine theta A equals NB sine theta B. So in the first material, this would be the index of refraction. Say this is where it's incident of the index for material A and the angle it makes in material A with the normal. This would be the index in material B and the angle that it makes in material B. Generally speaking, when light travels from a less dense to a more dense, we generally think that is meaning that the index of refraction of the first material is less than the index of refraction of the second material. It will refract towards the normal. So when this happens, it refracts or bends toward the normal. Okay, see what that might look like. Over here, we have material A. Over here, we have material B. Here's a normal. Okay. In comes a ray of light. I'm going to draw it coming in at roughly 45 degrees. There's theta A. Remember, we measure from the normal. It will bend, and it will bend so that it is closer to the normal. Here's theta B. Okay. Notice earlier I mentioned the fact that paths are reversible. If we go the other direction, if I go from more dense into less dense, it will refract away from the normal. So I can just reverse what we just said. If I change this so that I go from a more dense material to a less dense material, in which case the initial is bigger than the final, that changes the way my picture looks. If I'm going from something that is denser to something that's less dense, this might be like water into air. Air is less dense than everything except for a vacuum. Then if I come in, and I'll come in again at about 45 degrees. There's theta A. But this time, since I'm moving into something that's less dense, my refraction, it will actually bend away from the normal. So just by looking at the path, whether something is moving, refracting toward the normal or refracting away from the normal, I can tell whether or not it's entering into something that has a higher index of refraction and is more optically dense, like a diamond, or whether it's entering into something that is less optically dense. When it's less optically dense, like an air, it will move away from the normal. Obviously, it will travel in a perfectly straight line under two situations. One situation is if it comes in perpendicular. Okay. If it comes in perpendicular, the angle of refraction will be 0. That'll be 0. That'll be 0. It won't refract at all. Okay. If it comes in perpendicular. And it won't refract at all if it stays in the same substance. I'm not sure why you could think of a border from water to water, but there wouldn't be any refraction there. Most of the time when light hits a surface, we have both. We have reflection and refraction. Usually both reflection and refraction occur. If we think about this being air and glass, think about sunshine shining on a piece of glass. For a particular ray of light, what would probably happen, and again, I'll just draw one coming in at a pretty normal looking angle. If this is my incident ray, I'm going to call it theta A because it's over here in the first medium. Part of the ray will be reflected. We'll call that one theta R for reflected. Part of the ray will be reflected, but part of the ray will be transmitted. The transmitted ray will refract or bend towards the normal. So that's my reflected, and this is my refracted. Which brings up the question, how much more light is reflected than refracted, or what makes the difference? Generally speaking, the larger this angle is, the more reflection you get. I always like to think about like skipping a stone. If you drop a stone straight down, you know it will be transmitted and go right into the pond. But if you throw it at a really shallow angle, it might just glance right off the top. So generally, if I increase this angle, like this, the bigger that angle is, the more likely it is to be reflected. On the other hand, if I make it really small, like if I go straight in, like this, most of that ray will be transmitted. So generally, if we have small angles, or small incident angles, think close to perpendicular to the surface, we get most of the ray is transmitted or refracted. Most of it's going to pass right on into the new medium, right? Small incident angles, I have a lot of angles here, so let's here's my normal. Okay. So if I have a really small angle like this, I won't make it perpendicular, but pretty small angle, most of it's going to go right on through. Maybe I'll get a tiny little reflected, weakly reflected ray. But the closer I am to being at a 0 degrees incident or perfectly perpendicular to that boundary, the more likely it is to be transmitted. On the other hand, I'm going to do this other ray in a different color. If I have a ray that has a really large angle, so maybe it's coming in like this. That's a really large angle right there. It's going to be mostly reflected. It'll bounce right off that surface. although a small amount of it will be refracted. So with the angles really close to being to zero here, we're probably mostly transmitting it or refracting it. When this angle is really large, we're much more likely to be reflected. So at larger angles, more of the ray is reflected. When light travels, from one medium into another, the velocity or the speed changes. But the frequency of the wave or the light does not. Remember, the frequency of a wave, any type of wave, a light wave, a water wave, a slinky wave, is determined by the source. So even though the wave will slow down, its frequency does not change. If we think of our favorite equation for waves, V equals frequency times wavelength. When we think about light, let's assume the light is traveling in a vacuum. Well, it doesn't even really matter. We often write this as C equals F lambda when light is traveling in a vacuum. If the light's traveling in something else, this is more appropriate. But what we find is this frequency right there has to be a constant. What that means is if the velocity is changing, the wavelength is changing. If the velocity is changing, the wavelength is changing. If we want to think about this, remember we said that N is equal to C over V. And we're going to call this wavelength with the little zero, that's the wavelength in a vacuum. If it has the little zero, that's the wavelength in a vacuum. This is the wavelength in whatever medium it is. So the ratio of C over V is going to be F lambda 0 over F lambda. Those don't change. So we see the index of refraction is also a ratio of the wavelength in a vacuum to the wavelength in that medium. That's a direct consequence of this definition right here and the fact that our frequency is a constant. What that looks like then, if I draw a picture, draw right here. Let's suppose this is the vacuum and this is a piece of glass, some other medium. Our frequency won't change, so here's our wave. But when it hits that glass, it can't travel as fast. So the wavelength's going to get shorter. Okay? So the wavelength in a vacuum, from here to here, it's always going to be longer than what it is when it travels through something else. Okay? So N is not only the ratio of the speed in the vacuum to the speed in the material, it's also the ratio of the wavelength in the vacuum and the wavelength in the material. When you're doing your homework problems, pay particular attention to that, because sometimes they say we have a certain color of light or a certain X-ray and its wavelength is this much in a vacuum. And then they start asking you questions where it's in another material. And you need to be able to change the wavelength in a vacuum to the wavelength in the material. And this relationship will help you do that. Okay. I think it's time to solve a problem or two. We've got a lot of ideas. We haven't really solved any problems. Let's suppose that we have, I don't have the words, let me see. Let's just look at this picture. It's a good problem. This is water, and this is air. And here is our normal. And down here under the water is a little fish. Draw a little fish. Looks like a little goldfish cracker kind of fish. There it is. There's my little bitty fish. Okay? And light rays from this fish we'll draw the light rays right from the fish's nose. There's a ray of light traveling that way, 30 degrees. Notice when it hits air, air is less dense, so it's going to refract away from the normal. Okay, it's not going to go in a straight line. So here you are. There's your eye. There's your eyelashes. And you see a fish. You don't think the fish is right here, because what your eye does is it follows the ray back. And to you, it looks like the fish ought to be right here. Okay. This is why, if you've ever seen where it looks like you had a straw sticking in a glass of water or an oar in a boat, it looks like the straw is bent right at the surface of the water. And it's because the fact that this ray, whoops, let's draw it in blue, does bend when it leaves the surface of the water. In fact, we can calculate and find exactly how much large this angle is. Call that theta B. We're going to call it 30 degrees. That's our theta A, because we're going from water into air. So we're going from water into air. And we're going to have, here's Snell's law, NA sine theta A has to equal NB sine theta B. Well, the index of refraction for water is 1.33. sine. The angle that that light ray makes with the normal in the water is 30 degrees. That has to equal. Well, the index of refraction for air is the same as a vacuum. It's 1.00 sine theta b. So we can actually solve for this angle. Well, if we solve, we're going to get sine theta b equals 1.33 sine of 30 degrees. If I put that in a calculator, that comes out to be 0.665, 0.665. So I actually have to do a sine inverse. It's going to be the sine inverse of 0.665, and it comes out to be 41.7 degrees. So even though this angle, that's 41.7 degrees, okay? So when you look at something underwater, you can be misled not only about where its position is, you also tend to think things are shallower. They're actually usually a little bit deeper than they appear also. Okay? So that's a good example of how to solve for an unknown angle. I want to do another one. Okay, this example says I have a red laser and it has a wavelength of 633 nanometers in air. Okay. Okay. Lambda changes to 474 nanometers in the vitreous humor of the eye. Now, you may not know what the vitreous humor of the eye is, but it's basically the jelly-like fluid inside of your eyeball that helps keep your eyeball nice and round. So if you were to poke a hole in your eyeball, and don't do that, it's full of this jelly-type liquid called the vitreous humor, okay? And that changes the wavelength of the light. The question wants us to find quite a few things. It says to find N, F, and V for the red laser in the eye. Well, N is really easy. We can treat air like a vacuum. We know the index of refraction is 1, so we can behave. So really, N is just lambda 0 over lambda. So 633 nanometers over 474 nanometers. One of the things I didn't mention, but you're going to notice right here, is those units completely cancel out. The index of refraction is a unitless quantity. So 633 divided by 474 comes out to be about 1.34. Okay. So obviously the vitreous humor has an index of refraction very close to that of pure water. So obviously its main constituent is in fact water. The speed of the red light would be pretty easy to do. We know that N is equal to C over V, which means that V is equal to C over N. So the speed in air or vacuum is 3 times 10 to the 8th meters per second. Of course, we're dividing that by N, which has no units, 1.34. And that means that the speed in the eye slows down. It comes out to be 2.25 times 10 to the 8th meters per second. That's pretty much the speed of light in water or in your eye. And then finally, to get frequency, we know that C equals lambda F, or V equals lambda F. The frequency of the light is therefore the speed of light divided by the wavelength. And really we can do whether it's in the eye or out of the eye, it makes no difference. So I think I will use the fact that it's C over lambda 0. So speed of light is 3.00 times 10 to the 8th meters per second. The wavelength in the vacuum is 633 nanometers times 10 to the negative 9 meters. Notice the meters will cancel. Our units will be per seconds. It comes out to be 4.74 times 10 to the 14th hertz. That's a very typical range for visible light. Visible light is always between 400 and 700 nanometers in wavelength, and the frequencies are always on the order of 10 to the 14th. So if you're doing visible light you can see, red, orange, yellow, green, blue, violet, it should have a frequency on the order of 10 to the 14th hertz. Okay, that concludes the lesson and examples over reflection and refraction. Y'all, this is an extremely important section out of the chapter, so please do look over it a few times, review it. If you need help on the homework, just let me know. There you can see it without my shadow on the board.